of disordered interactive systems, rigorous insights from low dimensions. Eduardo, the floor is yours.
Thank you, Dario. Thanks for the invitation to speak here. It's not the first time, but I always enjoyed coming here. You talked about my PhD from '94, so 30 years since I graduated, I realize now. So I'm going to talk about disordered interacting electron systems, basically, but and I'll try to tell you why this is interesting and if we can learn a few things from the kinds of things that I've been doing. So this is work done with a bunch of collaborators. These three guys are former students. Iago Godoy and Luiz were my PhD students. João Getelina was José Abel's. And Victor and José Abel are professors in São Carlos and are collaborators in this work. So the outline of the talk is fairly simple. I'll try to tell you what is challenging when you study disordered systems, especially disordered electron systems. And I'll tell you about some of the outstanding issues in this area, issues that are not understood at this point. Then I'll tell you about this methodology, so-called strong disorder renormalization group, which is very powerful and in certain circumstances, and when it is powerful, you can actually reach conclusions which you can trust. And I'll try to explain why. And my focus here will be in transport properties in these systems. And I'll explain why this is interesting. So let me start by talking about non-interacting electrons in a disordered potential, right? So this is the famous Anderson localization problem, which can be defined in a very simple Hamiltonian. It's a non-interacting Hamiltonian. I'm talking about single particle states, okay? Where you have hopping between, you take a lattice, and you have hopping between sides of the lattice, and you introduce disorder, for instance, in the local potential that each electron feels. So this is epsilon j. It's distributed according to some random distribution, which does not have to be finely tuned. It can be general, okay? And what Anderson showed in 1958 is that this is a very non-trivial problem with very interesting properties. So he essentially showed the following. If you look at the states that come out of diagonalizing this Hamiltonian, you can sort of have a band of states, which is depicted here. This is sort of the density of states of the system. And the states that you get can be classified in two ways. The states in the center of the band are extended in the sense that they occupy the whole system. There is a finite probability of finding the electron or the particle anywhere in the system, although this is a disordered system. But he also showed that at the band tails, the states are localized. In other words, they are confined to a finite region of space with a finite extension, and they cannot be found away from that region where they are localized. And there is a sharp separation between these two kinds of states, such that if you fill up the states according to the Pauli exclusion principle, if your chemical potential falls in this area, you're going to have an insulator because the states that are available to the electrons do not reach from one side of the sample to the other, and therefore you cannot have electric conduction through the system. On the other hand, if the chemical potential is in the extended state region, this is going to be a metal, a disordered metal, but it's going to be it's going to have a metallic behavior, okay? And there's a sharp phase transition as a function of the chemical potential as you move the chemical potential through that so-called mobility edge, okay? Now, yes?
Ill-defined or not, I mean, it depends on P of epsilon, and you got these exact results. It sounds mysterious.
Let me qualify this further. Of course, if this is weakly disordered, then And it also depends on dimensionality. I'm going to tell you a little about this a little bit later. But if this is weakly disordered, if this is a very narrow distribution, then the region of localized states is going to be very small. Most of them are going to be extended. And it also depends on whether this is in 1, 2, or 3 dimensions. So I'm going to go into these details in the next slides.
Just tell me, I mean, where is it localized? Because there's nothing on the Hamiltonian that tells you anything is different anywhere you are on the system. So where is it localized?
Well, so there are 2 parameters that you can change here. You can change the width of the disordered distribution. So if it's narrow or if it's wide, that's one thing that you can change, okay? The distribution P. So
but it
P of epsilon, right?
Yeah, but it doesn't depend on J. It's not P of epsilon J, it's just P of epsilon.
J is the site. So you have a lattice.
Right. But you have different
So
P's
I have
at each
epsilon
site.
1, epsilon 2, epsilon 3, epsilon 4. And these are randomly distributed.
But the P doesn't depend on J.
No. These are
But then
what IID. So these are
No,
independently.
I understand, but where is it localized? Which J's are different from other J's? That's what I don't understand.
No, this is a lattice. The J is the lattice. So this is J equal to 1, J equal to 2.
I understand, but you say it's localized, which means it's restricted to some of the J's, right?
That's right. That's the picture here.
But
So if the energy that you're looking at, the eigenenergy of after diagonalizing this Hamiltonian, if it's in this region, that's what the wave function will look like.
I understand, but the Hamiltonian doesn't depend on J. That's the point. It looks like all the
J
J's
is the
are equal.
site index. J is like X.
No, I understand, but none of the parameters depend on J. You just have J sum over J.
Can I enter with a comment? Suppose that T is 0. Let's go to the limit equal to 0.
Yeah.
Then each eigenstate is exactly localized in one specific J. And you have for each J one eigenstate.
Yeah, but all the J's are equal. That's the point I don't
Yeah,
understand.
but you have a...
Each eigenstate has localized.
Suppose your lattice has 4 sides. Nathan. Suppose your lattice has 4 sides.
Yeah.
Just 4 sides. And you have epsilon 1,
Yeah.
epsilon 2, epsilon 3, epsilon 4. And as he suggested, let's take T equal to equal to 0.
Yeah.
Okay? Then you have 4 states, 4 eigenstates.
Yes.
One state here, localized, completely localized.
Okay.
One state here, completely localized. One state here, completely
I understand,
localized.
but all
But now you turn on T.
Okay, I understand what you're going to say, but all I'm saying is all sides of the lattice are equal. Do you agree?
In what sense?
That it's just
Each
as
site has its own energy.
It's just as likely to be localized at site 1 as at site 2.
Oh, yeah. So
okay,
this
okay.
localized state here
Okay.
is at one particular energy. If you go to the next energy, it's going to be localized in a different position of the system. Okay? Yes. And it's equally likely to be localized in anywhere. It's a random system. I think perhaps I should say a few words about this, but it's a little bit different from the usual Hamiltonians that you have, where you have a fixed Hamiltonian, a fixed lattice, and you have one possible solution or many different eigenstates and so on. This is an ensemble of Hamiltonians. In other words, if you have one realization where this guy, this guy, this guy, this guy is gotten after throwing a die, you have 4 values. But if you throw them again, even if it's the same die, it's a different Hamiltonian. So you have to talk about an ensemble of Hamiltonians. Okay? Okay, so now we go to experiments. The prototypical system where this was studied in the past are the so-called doped semiconductors. So this is a silicon semiconductor where you put impurities. Let's say phosphorus impurities. It can be boron impurities. It can be other stuff. These impurities will be randomly located in the system, and you can control their densities. So you can have low density of impurities or high density of impurities. Excuse me. If you have high densities, there's a large probability of this guy to jump to the next one, to jump to the next one, and so on. And remember that this is probably better modeled, not by this Hamiltonian where you put disorder here, but in a Hamiltonian where you put disorder here. Because depending on the distance between the impurities, you're going to have a different hopping between them. Okay? But in the language of the universality classes, after many years of studies, we know that these 2 kinds of systems are in the same universality class. So it doesn't matter much if you put disorder here or disorder there. But anyway, you can have this situation, you have many impurities, it's favorable for you to hop and you have a metallic behavior, whereas if you have few impurities, it's going to be harder to hop, and there's a higher tendency to localize. And that's actually what's seen in experiments. So this is precisely the conductivity at 0 temperature, extrapolated to 0 temperatures as a function of the concentration of impurities. So for high densities, it's a metal, it's a finite conductivity, but as you decrease the density, you go to a situation where the conductivity goes to 0. The conductivity at 0 temperature is 0. In other words, you have an insulator. And this is all scaled by the critical conductivity, which is going to depend on the sample and so on. But this behavior is very typical of usual critical phenomena of second-order phase transition in critical phenomena in, let's say, magnetic systems. And as in critical phenomena, you can actually measure the critical exponent with which sigma goes to 0. And there are two different cases, a so-called uncompensated case, where I have only one type of impurity, and this exponent is around 1/2. And the compensated, where you have electric donors and hole donors, so the number of electrons available for the impurities is different from the number of impurities. So this is the compensated case where mu is equal to 1. So the difference between these two cases is the number of electrons per impurity, essentially. So in the first case, this is 1. In the second case, you can tune. And these are the two exponents. Now, you can study that Hamiltonian, which is, as I said, very simple, with very large computers, supercomputers, and can calculate this exponent for this kind of system. And the numerics at this point is essentially exact, okay? And this exponent calculated through numerics has nothing to do with what's measured in the lab. Very different. So what is going on here? What can explain this difference? And the best guess that we have is interactions, because electrons in this system are interacting with one another. They are not non-interacting electrons, as in the Anderson model.
Sorry, just, a small. The number that you reported by Slevin and Otsuki is for the 3D Anderson. Okay, that is the one.
Yeah. Okay? And I also want to point out the following. The best, yes? Okay, mu here is the critical exponent of the 0 temperature conductivity as a function of the density. What do you mean? This is the conductivity, the electric conductivity. This is the density of impurities.
No. My question is about the mu. The
mu is the exponent. This is a critical exponent. But just like you have, a magnetic system, you can calculate the critical exponent, let's say, of this magnetic susceptibility as you approach the ferromagnetic transition. There's a non-trivial critical exponent that's usually calculated with renormalization group methods. This is a second-order phase transition. Okay. Every second-order phase transition is characterized by critical exponents that define the universality class of the transition. That's what's being done here. Okay? Now, I call your attention to the so-called nonlinear sigma model, which is the best theoretical tool that's been used along the years to calculate this exponent. Essentially, this is a perturbation theory in disorder. And the best, this is almost like QED. This is a 5-loop calculation, and the exponent you get is this one. Now, this is the correct exponent. This is the exponent that the nonlinear sigma model gets you. So not only the real system is probably not well modeled by the Anderson Hamiltonian, and you need to include interactions, but also the available technique is not very good at studying the Anderson model. Okay? Now, going further, now coming back to your question.
Do you have an idea? Because instead...
Idea of what?
No, I'm going. Because instead, let's say, the cavity method, which is essentially the same of the sigma model, works very well for the beta lattice. So here, what is the point? They are discharging loops like...
yeah, the loops change the universality class.
The loops
completely.
in the geometry, you say?
Yeah, yeah.
Okay,
The
so-
beta lattice is essentially infinite dimensional.
Exactly.
So this is the exponent that I showed is 3 dimensions.
Okay.
You can, have these exponents for 4 dimensions, 5
Okay,
dimensions. so on.
okay.
Okay?
So become better and better when you go up in dimension.
Yes.
Okay.
I actually have a paper on this. I'm not going to talk about
Okay.
it anyway.
Later, yeah.
Anyway, so since the early 60s, it's been known, for instance, that in 1D, there is no Anderson transition. In other words, any amount of disorder, no matter how small, will localize the system. All the states are localized. There are no metallic states in 1 dimension. Now, in 2D, there is this famous result called Gang of 4 paper. This is an extremely important result from 79. This is a so-called beta function for localization. And this paper showed that there, also in 2D, you don't have a metal-insulator transition, at least for the usual Anderson model, and all the states are localized. Now, in 3D, there is a transition for sufficiently strong disorder. So the density of states that I showed with localized states and extended states is only valid for 3 dimensions or above. Okay, below 3, everything is localized. Yes?
Let me just try to understand. So the statement is that in 1D, unless you put all the epsilons to be exactly the same, it will be localized. But if I put all epsilons the same, then it is a metal. Okay.
Then it's not disordered.
Okay, okay.
What I'm saying is that if the distribution has, no matter how small
Spreading
a spread, it's going to be localized. Of course, there is one thing called localization length, which is the size of the wave function. Of course, if the disorder is very small, the localization length is very, very large, and you have to go to very large systems to see that it's localized. But the answer here is the following. In the thermodynamic limit, everything is localized in 1 and 2 dimensions. Okay? And I should mention also, this result is completely general. It's essentially a result of waves propagating in a disordered medium. So this is not confined to quantum mechanics. It works for acoustic waves. I would say electromagnetic waves, although electromagnetic waves have polarization, and that's a more complicated problem, but scalar waves in a disordered medium will have this phenomenon as well. Okay?
Maybe I say something that is completely wrong, but would you say that in 1D, all are localized? Isn't that equivalent to the statement of Van Hope that there is no phase transition in 1D?
Statement of, like Landau, for instance, no finite temperature phase transition in 1D? Is that what you're talking about? Which is true.
Yeah.
If you take,
because those cases require certain conditions on the potentials.
yeah.
Which is
So
not this.
if you're talking about finite temperature phase transitions, that's not what I'm talking about. This is a quantum phase transition. It happens at 0 temperature, okay? But you're right that I should be more rigorous and qualified. There are situations in 1D where you can have a transition. For instance, if you have, so I'm assuming that the distribution of this guy is completely independent from the distribution of this guy. In other words, identically and independently distributed variables. This is the assumption that I'm making here. If you introduce correlations among the variables, in other words, the probability of this guy assuming a certain value depends on the value of this guy. And if these correlations are long-ranged, then you can have a transition even in 1D. But it's questionable whether this situation applies to real systems, which is why we usually don't talk about this, but yes, you could have a transition even in 1D if you introduce disorder correlations, as they are called. But I'm assuming what is usually called IID, independently, identically distributed random variables. Okay?
maybe I have a dumb question, but because you say that the transition that you look is in 0 temperature, right? So, but if you look to that which is something magnetic impurity, you can have condo effect. So you cannot look for that temperature. That's not a problem. I don't know.
You're talking about many different things at the same time. Yeah.
Right.
Okay. The condo effect is the effect of. It's not an effect of the sword. It's an effect of interactions.
No. Yeah, but if you look to that, because if you look to the transition in some insulator which dope with the magnetic impurity, in principle, you can have condo effect. So you cannot look to the 0 temperature. That's my question.
But the condo effect is usually looked at as a function of temperature. It's the quenching of a local moment as you decrease the temperature. At 0 temperature, if there are independent condo effects, all the magnetic impurities are quenched by the conduction electrons, okay, at 0 temperature, which is what I'm focusing on here. But this is a different story. Okay, you could talk about magnetic disorder. It's a different universality class, but even without the condo effect, that's an interesting problem. But that's not the problem I'm talking about here. I'm talking about so-called potential disorder. In other words, it's just the values of the Hamilton. You can define the problem without spins. Actually, I didn't put spins there, right? Okay. You can define it for spinless electrons. But as I said, you are right in the sense that you could consider other types of systems with spin orbit interaction, and so on. And actually, the beta function for those systems is actually different. Okay. So it's an interesting point. But I'm considering potential disorder.
So here, that doesn't matter for, okay.
For the kinds of systems I'm looking at, it doesn't matter. But as soon as you put interactions, it starts to matter. Because interactions changes the game, completely changes the game. Then spins are important and so on. Okay, but at this point, no interactions.
Okay, thank you.
Now, as I said, theory forbids a transition in 2D. But look at the results on MOSFETs that became very famous in the late 90s and early 2000s. This is a typical transition. This is resistivity as a function of temperature for different concentrations of impurities in a 2D system. These are MOSFETs. These are the things that run our computers. The transistors in our computers are driven by MOSFETs. There's a clear transition here as you change the concentration. It is a typical fan behavior when you have a second-order phase transition. And yet, theory says that this should not occur in a non-interacting system. Okay, so obviously, this is probably due to interactions also. And as a matter of fact, if you make an estimate, this is in silicon, basically. We know everything about silicon. So if you make an estimate of the kinetic energy of the system and the Coulomb energy in the system, the Coulomb energy is 1 order of magnitude higher than the kinetic energy. So it's no wonder that interactions are important in this system, okay? So the Anderson model is not enough for this. And finally, even if you go back to the doped semiconductors, this is a result from the 90s. If you look at the magnetic properties, this is the magnetic susceptibility. It is diverging with a non-trivial power law as the temperature goes to 0. Okay, that's one thing. So the magnetic behavior of the system, coming back to you, is non-trivial. And what's more, this is in the metallic phase, and this is in the insulating phase. You cannot distinguish the system by looking at the susceptibility only. You cannot say whether it's a metal or an insulator. Okay? So in a sense, you have probably 2 points. If you increase disorder, you have at low disorder what's called a Fermi-liquid metal, normal metal, disordered metal. You have a point of perhaps a transition. It's unclear whether this is a transition or not, where the susceptibility at 0 temperature is diverging, but the system is still metallic. And then as you increase disorder further, you reach a point where you go into the insulating phase, and you have a metal-insulated transition. Okay? And there is no way you can explain this without interactions. In other words, putting it all together, these are just 3 mysteries. There are others, but these are probably the most important ones, that tell you that the disorder plus interactions is an open problem in condensed matter. Okay? So what I'm going to try to tell you in the second half of my talk is how to use, how to try to get insights into the disorder plus interaction problem using a technique that works very well in low dimensions. It's less so in high, or it's more complicated to use it in higher dimensions. It's not that it can't be done, but it's just harder.
Sorry, what is the distinction between low and high? Let's say low is 1 and high is already 2, or...
everything I'm going to talk about is 1.
Okay.
It's basically, well, the thing is that in 1, you can do a lot of stuff
Exactly.
analytically.
Exactly.
In 2, you have to do computer.
So
you can do it.
So this method works well. When you say low dimension, you mean 1 dimension.
Once again, if you want to do analytically,
Okay.
1D.
Okay.
You can do numerically in higher dimensions.
And it works well still.
I'll give you the conditions under which it works. It doesn't work always, okay? In fact, there are systems where it's very hard to apply the method even in 1D, okay? Yes.
Do you know about the upper critical dimension and what's the...
Well, for the localization transition, there are conjectures, just localization, Anderson insulator, is infinite. The upper critical is infinite.
That's bad, okay.
The lower critical dimension is 2, as I said there. The upper critical dimension is, there is controversy about this. It's not clear, but I would say that most indications are that it is infinite.
Okay, okay.
So there's no 4 plus epsilon or 4 minus epsilon, whatever.
Okay, okay.
Okay? Okay, so I'll first start by describing the method so you get a feel for the method, although I will not apply it to this Hamiltonian, but applications to other Hamiltonians will be reasonably easy extensions of the method. So I'll take a Heisenberg model, let's say spin a half. So you have spins on a lattice. I'll take a 1D lattice. And they are connected by random exchange interactions. Once again, IID, in other words, independently, identically distributed. Okay, so there's no correlations, J1, J2, J3, and so on. I want to solve this problem. So there's only one assumption here, which is that the J's are all positive. You can relax this assumption, but then you are in a different universality class. If I have time, I'll talk about this towards the end. But in this case, I'll focus on distributions which are, in principle, any distribution, but they have support only for positive J, okay? In other words, antiferromagnetic interactions. The spins want to be anti-parallel. And there's omega is sort of the high energy cut of the distribution, the largest possible value of the J's. So how do you solve this problem? First of all, I'm going to solve it for one single realization of this order. In other words, as I said, if you throw your dice many times, you have many different Hamiltonians. Let's fix one particular realization, one particular Hamiltonian that has the characteristics that I described. And you look for the highest J in the sample. The highest J is going to be omega, which is a high energy cutoff of the distribution. So these two guys are going to be coupled by an extremely large coupling, which I call omega. And if you diagonalize just these two guys, you have a ground state singlet, an excited triplet, separated by omega. At low energies, and my method is good at low energies, this will never be excited. So I'm just going to exclude the triplet from that bond, but then I'm going to do something else. I'm going to do perturbation theory on the adjacent couplings, which I call J1 and J3, okay? And of course, if this is the largest scale, these are going to be, well, they're certainly going to be smaller than omega, and in general, perhaps even much smaller than omega. And you can do perturbation theory. You can show in 2 lines that there is an effective coupling between S1 and S4 after you eliminate the pair, the strongly coupled pair. And the new coupling that's going to couple these two guys has this form, J1 times J3 divided by 2 omega. In other words, the new coupling is smaller than the previous J1 and J3 couplings. So in the process of doing this decimation, I got rid of 3 couplings, omega, J1 and J3, and I introduced a new coupling, J prime, which is smaller than the other 3. And as I said, the net result is that S2 and S3 disappear. They don't disappear. They form a singlet, and a singlet is basically inert to anything, okay? And you introduce a new coupling, and in 1D, the topology is maintained. In higher D, it's not going to be the same. But in 1D, the topology of the couplings is restored. If the infinite system, you get the same system back again. And you do this many times. So you iterate. So physically, what I'm doing is that at each decimation step, I'm eliminating couplings, which are here, here, and here in general, and I'm putting a coupling down there. So if you start with this hump, you take stuff from here, you put stuff here. And this is the result of an actual simulation. This starts from a uniform distribution, and the process of doing this over and over again generates a distribution which is extremely singular close to j equal to 0. In fact, you can now analytically show that there is a fixed point to this flow. Notice that different from other applications of renormalization groups, where you have 1, 2, or 3 couplings, and you study the flow of the couplings, here you have a distribution of couplings, and you study the flow of the distribution. And you can show that there is a fixed point distribution that has this form. It's a power law with an exponent 1 minus alpha, where alpha is actually always going to 0, slowly and gradually approaching 0, logarithmically, as you decrease the coupling. So omega 0 is the initial coupling, omega is the coupling as you go down. Okay?
Sorry, how is defined, because you showed us how to find, how to find omega or omega 0 numerically for a fixed realization, but this omega must be, what is this omega? Cannot be...
Okay, so if you look at here, I'm eliminating distributions on this end. So if you eliminate a certain weight, the omega 0 that was here becomes here.
I agree, but that is
so
for a particular realization. This instead is in terms of the distribution. So,
yeah.
So this omega must be...
No, if you have one realization, there's always going to, in a finite system, there's always going to be a larger one.
Agreed.
And you decimate it, there's a second largest, and it goes down. If you do this for many, many systems, many, many realizations, you can talk about distributions.
Exactly. So
and
this omega in terms of distribution is a function of what?
What? Excuse me.
I mean, for this analytical formula, omega is a function of what?
Is the RG scale that's going down. It's the RG scale.
Okay.
Okay, the distribution is always cut off at omega. And omega is going to 0.
Okay.
And you look at the form of the distribution as you go to 0.
I see. Okay.
Okay? So you can show that this is a fixed point of the equations. You can show that it's an attractive fixed point. You can study irrelevant operators around this fixed point. It's not the only fixed point, by the way. There is another one, which is probably unphysical, but there is another one. Okay? But so probably all the other reasonable initial, and there is numerical evidence for that, initial distributions flow to this fixed point here. Okay? And the characteristics of this fixed point is, most important one is this one here. If you take the dispersion in J divided by the mean J, so in other words, standard deviation divided by the average, it goes like 1 over square root of alpha, and alpha is going to 0. In other words, the width of the distribution compared to the average is going to infinity. In other words, the distribution becomes infinitely broad as you scale down. Just a second. In other words, the effective disorder, which is measured by the flowing distribution, becomes infinitely large, infinitely broad. Okay? Now, I also should mention the following. Because it becomes infinitely broad, the decimation procedure, which is gotten through second-order perturbation theory, becomes asymptotically exact. Okay? Because you just look at the conditions for validity of the second-order perturbation theory. Of course, it's not always a good approximation, but as it becomes very broad, it becomes asymptotically exact, okay? So the method is said to be asymptotic when the distribution has this behavior. It's not always like that. So this comes to your question. But when it does have this behavior, the method is asymptotically exact. And it has been applied to the transverse field Ising model in 1D, which is the only distorted model that has an exact solution, the so-called McCoy-Vu solution. And there's one quantity that you can calculate with exact methods and compare to the method as applied to that other system, and it gives you the same answer. So at least in this case, there is reason to believe that asymptotically the results are exact, even though it's a distorted system, which is usually very hard. Okay?
Does the system have a solution if it's finite?
Not an easy one. No. It's a hard problem. Of course, it's famous that the non-distorted problem, the uniform problem, is the famous Bethe solution of 1930. He solved the Heisenberg model for spin-a-half, launching the Bethe ansatz in 1930, and that's the problem without disorder. Okay.
In the usual RG, you linearize the renormalization group transformations to find, for instance, critical exponents and things like that. Can you do something like that?
Yes, you cannot for this system. The system does not have a transition. The system that I showed you flows to a fixed point. This is a fixed, the basin of attraction is probably all distributions except those singular ones, and they all flow. This is a stable phase. It's not a transition point.
But
the Ising model...
But the Ising model, yeah, you can...
yes, you can calculate everything.
Extract,
yes. You can actually check, for instance, this famous Harris criterion, Chase, Spencer, and Fisher bounds on critical exponents for disordered systems. It checks everything. It works for everything.
Okay, got it.
But there are systems where it doesn't flow to infinity. And then the method is not justified, okay? Just want to mention that. Yes?
So I don't know if this is physical, but so suppose P of j is just delta functions. It can only be, let's say, 3 different j's. And it randomly picks one of these j's.
Goes to this.
No, but how can it go? You're assuming one of the j's is 0? I mean, how can it flow? There's no flow. It's just discrete.
Of course there is flow. You're talking about the distribution like this, I suppose. I don't know. Correct me if I'm wrong. You're talking about the delta here and the delta here.
Yeah.
For instance, okay? So if you make a realization, you're going to have J1, J1, J2, J1, J2, J2. That's the one realization of this. Yeah. Now, if you take the largest one, of course, in this case, it's hard. It's a little bit hard because there are many couplings that have this value. So it's hard to define one only that's bigger than. But if you give it a little bit, for instance, of width, then there is a highest one. Okay. And then you can do the procedure. And what's going to happen is that you're going to fill up this gap, and you're going to go to that distribution also. Okay? It's a little bit pathological for the method in the sense that there are many couplings there, but okay.
We have another question.
Oh, okay.
So I think that perhaps is related with the question of Dario. So I have a distribution, right? So I make a realization of my distribution. I pick up the greatest one, and I start to making the flow by dropping out terms and keeping with the singlets. So what is the necessity of having like a max cutoff in your original distribution? What happens if I have, for example, a polynomial decaying solution?
I'm pretty sure that, it's a little bit like this one here. It's hard to define a larger one.
Yeah.
But if you have, for instance, a finite system, there's always going to be one largest coupling.
Yeah.
And I'm pretty sure that if you have distributions which are, let's say, the fall off sufficiently fast, the method applies as well. You probably have to change a little bit things and perhaps work with finite systems and study it as the system goes to infinity. There are these complications, okay? But I don't think they are essential. I don't think they're
Yeah, the question is because at the end, so mathematically you have like a family of fixed points for your distributions when you make this kind of decimations that is equivalent to saying some kind of central limit theorem. And
No, not sure, not sure. There's only one fixed point, which is that one.
yeah, but that fixed point is like having a alpha zero of a Levy.
No, no, okay. You might argue that this is not a fixed point because it's not fixed. Alpha is varying. But you can't define a bona fide fixed point for this problem. It would take me a long time to do this here. But you can, if you rescale the couplings to the cutoffs, the function, the rescaled function, has a bona fide fixed point that does not move as you lower the cutoff.
Yeah, because
I don't have time to go into all
like,
these details.
Like, kind of unexpected that at the end you have a well-defined disorder, original disorder with your like finite variance and so on, and while making this procedure, you end up with a distribution that has infinite variance that is completely.
Right. That's the beauty of this thing. You put your finger on it. That's what's interesting here. The reason is what I said here. You take things from here and you pile them up here, just like this thing is showing. Okay, so no matter how you start here with a uniform distribution, but you are always piling up stuff at close to j equal to 0. So in a sense, what happens here is pretty much irrelevant. What's important is the thing that's happening down there at low temperatures. And this is going to govern all the low temperature properties of the model. Okay, but this is, as I said, apart from this sort of pathological initial distribution, this is the only fixed point of this problem. Okay?
You end up with a system which is super ordered and free, right? Because the interactions are peaking at j equals 0, right? I mean,
super ordered?
in the sense that all j's are 0.
No. It's precisely the opposite. It's super disordered. Because see,
that distribution that you're showing seems like there's a huge peak at
you
j
should look
equals
at this thing here.
Okay.
You should look at it. This is the width divided by the mean, right? The width divided by the mean is 0, means no disorder.
You should rescale that one.
That's right. You have to rescale because both of them are going to 0.
Okay.
But one is going to 0 faster than the other. You have to rescale. As I said, if you do sort of the correct procedure or rescale quantities appropriately, then everything becomes clear. But this would take a long time to explain. It's not difficult, but okay? So I'm not going to tell you about this, but because you put your finger on something important, that most of the J's are very small. And so if you are at low temperatures, let's say at a certain value, most of the J's are going to be much smaller than temperature, and they're going to be free. You're right. And with that kind of reasoning, you can actually calculate susceptibility, specific heat, entropy, and so on, and the system. And these are believed to be exact, asymptotically exact. Okay? There is numerical confirmation of this. Now, my focus, I don't have time to talk about, but it doesn't matter. I think it's fun to discuss this thing. My focus is to look at dynamical quantities, in other words, frequency-dependent quantities for this kind of systems. And you can do that. You can apply the method. You have to sort of extend what I told you so far to, let's talk about frequency-dependent conductivity. So this is a so-called Kubo formula that you get from linear response theory for the frequency-dependent conductivity of a certain system. And you can apply the RG to this formula, in a sense. The only thing is that I have been telling you about these energies here, because as you do the procedure, you generate all these energies of the strongly coupled pairs. But you can just do the same thing for the matrix element also. It takes more calculations, but you can do this for this. And you can have access to the frequency-dependent conductivity. So for instance, you can apply this to the Anderson model in 1D, where we can do things analytically. As I said, you can do this in any D. My paper that I told you about, the higher critical dimension, for any dimension. For non-interactions, it's easy. When you put interaction, it's not so easy, okay? And the current operator in this case is basically the hopping term. And you can put it in the Kubo formula, and you can do the RG and calculate this quantity. And what's nice is that you can recover, this is a very old result for the frequency-dependent conductivity in the insulating phase, so-called Mott law, which is given by omega squared log squared. And we can obtain exactly this using this procedure, including the log correction, including the correct exponent of the log, okay? So it works. Now, here's the first interesting problem I want to tell you about, which is the so-called XXZ model, so back to spins now, okay? And you have not the Heisenberg model, but you put the coupling between spins along the z direction different from the coupling in the transverse direction. So this is the so-called XXZ model, spins a half, and disordered. And you can define a so-called spin current operator, which is just the thing that moves your up spin from one side to the other. So you...
Lots or?
It's 1D, 1D.
Okay.
Okay? And you can apply the same methodology. And this was done way back in 2001. And these guys concluded that this is a disordered system, a one-dimensional disordered system, whose conductivity goes to infinity as omega goes to 0. In other words, a metal. Which is very strange. Even though it's not non-interacting electrons, it's very puzzling that you have metallic behavior for this system. And we were very puzzled about this, but I'll tell you why this is puzzling. This problem can be mapped to fermions using the so-called Jordan-Wigner transformation. So this problem is equivalent to this problem here. So this is hopping. You have disorder in the hoppings, and you have interactions, spinless electrons and interactions, okay? Now, because of the interactions, you might think that, oh, okay, it's metallic because of interactions. Okay, we don't know how to explain this, but it's possible. However, if you put delta to 0, this is a non-interacting problem. And this is a well-studied non-interacting problem where we know that the states in the middle of the band, which is what we are looking at here because this system has no particle hole asymmetry. We're looking precisely at the middle of the band. The state is localized. So it should be an insulator.
I thought that the method was good close to the ground state, but here you are really looking at the highly excited states, right? Because you are...
No. Because I'm always decimating. The cutoff is always moving to 0. So I'm always looking at low energies.
Okay, but
it's only asymptotically exact at low energies.
Sorry, but so what does it mean at the center of the band? At the center of the band?
Because here it spins. There's no bands, just spins.
Okay.
But when you map it, you have a fermionic problem.
Sure.
But there's no chemical potential here. So this is a particle hole symmetric fermionic problem, which is why I'm saying that of course you could get all the spectrum here, as you could get there. What I'm saying is that the low energies of this guy correspond to the center of the band of this guy.
So the highly excited. The highly excited states of the other guy. Center of the band are highly excited, no?
No, because there's no chemical potential. Okay, this is 1D model. Let's say density of states is like this, but this is mu equal to 0. There's no mu there. If you put mu there, it's a different problem. Okay, there's no mu there. Mu equal to 0. So you are at the center of the band.
Okay.
Okay? If you want to fill, you have to translate spins to fermions. If you want to fill the fermions up to here, you have to put a chemical potential. If you don't put it there, and then it's a different problem. Okay? And it's been known since a long time ago that these guys are localized. But notice that usually in localization, the wave function is like this, where this is the localization length. So it falls like there's an envelope that decays exponentially with the width, which is this localization length of that particular state. What I'm saying is that in this case, There's a square root there. So it's a little bit sort of an extended exponential. But still, it's exponentially localized. There's no doubt that this is exponentially localized. So the question is, what's going on? How do they get metallic behavior at delta equal to 0? They actually get it for delta from 0 to 1. To 1. And how do they get that if we know that the states are localized? The question, the answer is in the literature for many years. And the problem is that, once again, this is a disordered problem. You have an ensemble of Hamiltonians. And whenever you have a disordered problem, you have to ask yourself whether the quantity that you are calculating has a wide distribution or not. In other words, is it self-averaging, which means that it's delta function distributed, or whether it fluctuates a lot. So you have a sample here, you measure it as one value, another sample, same disorder, but another sample, different value. Okay, so in 1D, this is very well known that the conductance, and with the conductance, the conductivity is very broadly distributed. And the average value is much larger than the so-called typical value. The typical value is the following. I like to give the following example when I want to distinguish between average and typical. You take 100 things. And the values of these things, 99 of them are 10 to the minus 5. And one of them is 10 to the 10th. You calculate the average, it's going to be extremely large. It's going to be dominated by the one instance where you get 10 to the 10th. But the typical value is 10 to the minus 5. If you take one random one, put a gun to your head and say, what's the value of that one? You're going to say 10 to the minus 5. You're not going to say 10 to the 10. So why? Because it's an extremely broad distribution. And the typical and average values are very different. And computationally, the typical value, you could define it through the median of the distribution, the most probable values. There are very different ways, but the easiest way, computationally, to get at the typical value is the so-called geometric average, which is you take the average of the log and exponentiate it. If you work out, this is just the definition of the geometric average. And in 1D, the conductance is not self-averaging. It's widely distributed, and the average value is much larger than the typical value. So from the start, we thought we have to look at the distributions. Okay, and that's what we did. These are the distributions that were calculated for that system. Now, look here. This is, I define this quantity gamma because everything here happens on a log scale. So it's not good to work with omega, sigma of omega, but look at this gamma scale here. And as omega goes to 0, gamma goes to infinity. So low energies, just a second, low energies here, you should look at large values of gamma. And these are the distribution of conductivities as you increase gamma. So when gamma is large, in other words, low frequencies, low, this is the distribution. This is a log scale here. So it's many decades of values of sigma at low energies. Even if you start from a distribution which is not very large, it broadens as you go to low energy. Yes?
Yeah, can you go one slide back, maybe?
One slide back?
One slide, yeah. Yeah, this one. This one, yes. This paper by Hughes and collaborators there, what did they do there? What kind of approach did they use?
They just calculated the average. These are very smart guys. I don't know.
Yeah, okay. Okay.
I don't know. And so if you look at the distribution, it's extremely large, okay? So it points to this kind of behavior here. The average value is very different from the typical value, okay? And you can actually scale the average value if you rescale both axes with square root of the size of the system. Everything falls onto the same curve, and you can, for different sizes. But if you are, for instance, in this region, now remember, once again, don't forget, gamma should go to infinity. Gamma going to infinity is omega going to 0. So the fact that this thing is blowing up with gamma is the metallic behavior that they found. Okay? It goes down because of finite size effect. If you have large systems, this thing goes to the right, always to the right, which is why when you rescale like this, they all follow the same curve. So in this region here, you are in the metallic behavior of the average conductivity. Okay, so you should focus on this region here. But then, if you look at any value inside of this region, and you look at the typical conductance for these different sizes, you see that it's going to 0. So you fix omega, for instance, you are, according to the average, a metal, but the typical behavior is going down. So there is a wide separation between average and typical values. This is very common in this kind of system. Okay? And, okay, so in a sense, our conclusion is this is not a metal, this is an insulator, as we expect. So even though you can put interactions in this case are not enough to turn an insulator into a metal. Okay? You have just to be careful. And you can check this against exact diagonalization. It's reasonably okay. But with exact diagonalization, you cannot do large systems, even if it's non-interacting. And, well, my time is up. But let me
I don't know if you have time and willing to. For the exact diagonalization, what do you need? You need the full spectrum. You need. I mean, this is just a technical question.
No. So this is the exact diagonalization was done for delta equal to 0. In other words, non-interacting line.
Right.
Otherwise, you cannot do like more than 10.
Exactly. No, my question is, do you need the full spectrum or you need just few eigenstates? Or to compute the relevant quantity, you... Well, we can chat later. I mean, it's not important.
I think you do. I don't know if you need the full spectrum, right? We calculated the full spectrum.
Okay. No, my question is because
perhaps
numerically that can change a lot. So if you don't need the full spectrum, you can do much better. So
sure.
Okay. Yeah.
But I think this was, let's say, unsophisticated enough that we probably did everything.
Okay.
I really don't know. This was done by the other students of my collaborator, and I was not so much into the details of that computation.
Sure.
But this is a free formula, so it's just diagonalize, calculate the Kubo formula, and that's it.
No, because let's say the number is not so crazy large.
No,
if you,
it's true. Yeah. It's true. Probably go further than that. Okay. Now, in the 0 minutes that I have, I just want to flash this because in the back of our minds, our question was always, can you find a system that otherwise should be localized, but because of interactions is localized, but because of interactions becomes metallic? Okay? And the answer is yes. And at the beginning, I told you about this Heisenberg model where J is always positive. But you can also study the case where J can be either positive or negative. In other words, the coupling constant can be both anti-ferromagnetic or ferromagnetic. It's a little bit more complicated. The phase is completely different that you get. And it's easy to see why, for instance, if you have two spins, 2 and 3, with the largest coupling, if this coupling is positive, you have what you had before. Okay, you form a singlet, and you can calculate the renormalized coupling very easily in perturbation theory. But if the coupling is negative, you form a spin 1. Right? The ground state of two spins 1/2 coupled ferromagnetic is a spin 1 ground state. You have excited state, but the ground state is a spin 1. So if you do this procedure here, you're going to have to take care of different sized spins because they are generated by the RG. You generate spin 1, then the spin 1 meets a spin 1/2, can generate a 3/2, and it goes on. Okay, this was done long ago by those people there, and this phase is called a large spin phase for obvious reasons. So the sizes of the spins have a distribution which is very broad, and it can, for instance, the average size grows with the square root of the size of the system, and it's actually a random walk. You can explain this very easily. It goes with the square root of L. So the average size grows, and the distribution is large. Large spin phase. Now, for spin 1/2, you can do Jordan Wigner, and the initial system. So you start with an initial system with spin a half. You can map this to that, just like we did before. But notice that Ji can be positive or negative. The sign of the hopping term is irrelevant. This is gauge. You can gauge it away. But the size of the interaction term is not irrelevant. One is attractive, the other is repulsive. Okay? And the fact that you have both repulsive and attractive interactions in that model is what's behind what's going to happen. Because what we find is that this system does indeed seem to have a metallic phase. Okay? So you calculate the conductivity, for instance. This is the average conductivity, I think. Yeah? As a function of this famous gamma. So once again, remember, gamma goes to infinity as omega goes to 0. So you see that it's going up. You can actually calculate the behavior. It's given by this non-trivial exponent, which is non-universal and depends on the initial disorder distribution. So this is a different story from the antiferromagnetic system that I talked about. But this is the average conductivity. You might find this not enough. You should look at the typical one. And even the typical one has this kind of behavior. Once again, the fact that it goes down after a certain value is a finite size effect. If the size of the system grows, the maximum moves to the right. In other words, to lower energies. And this system is a metal, a spin metal. Okay? Now, let me make one final comment about this, which is the following. If you think physically in terms of the fermions that I started with, I said that there are fermions and there are attractive and repulsive interactions. Now, there is one way you can beat disorder, which is with attraction, which is basically a superconducting state. A superconducting state is a state that has no problem with modest amounts of disorder. Well, it depends on the situation, but by and large, you can introduce disorder in the superconducting state, and it remains superconducting. So you might think that, oh, this is just a superconductor. But I warn you that the fact that I have both repulsive and attractive interactions is a different problem. Because if I had only attractive interactions, then I would agree with you. This is a superconductor, the usual superconductor in 1D. But this is a different phase. This is a different phase. If you put just negative J's, you do not get this phase. This is a different phase. Okay? But, okay, I admit there are attractive interactions at play here, and obviously they are important for the physics that is found here. Okay? And I think that's basically it. This is the distribution that I get on a log scale. They are large, but they do not get extremely large as gamma grows. Okay, they do grow, but not too much. It's very different from the other case that I showed. And finally, I think I didn't go much further than my time. So the main message is that disorder plus interactions is an open problem in condensed matter. Of course, interactions alone is also an open problem. But if you put disorder, there are many specific problems related to the disordered systems that are completely open and not understood. And what I think is nice about the applications I showed here is that you have a method that you can trust in certain situations, not always. But there are situations where you can trust the method. And as I showed before, the nonlinear sigma model is completely untrustworthy. At 5 loop, it's far away from the exact value. Okay, so I think it's at least one should give a chance to this other kind of methodology. And as I said, I mean, you have to be very careful when you have disordered systems to determine whether your quantity of interest is self-averaging or not. It's very important, because if it's not, you might be misled in your conclusions. And that's it. Of course, the basic challenge is to go to a higher dimensions. It's much more complicated in higher dimensions, I have to say, okay? But it's not impossible. I have to find the correct problem to work on. Okay, thank you.
Okay.
Thank you very much. It was one of the most active colloquia that we had in the recent past.
That's wonderful. I like it.
More questions? Okay, many. Let's start.
So one thing that hasn't convinced me is why these models of P of epsilon describes impurities. Is there any matching with experiments?
Oh,
that
yeah.
you can show? So which ones can you match
For
with
instance,
experiment?
Let me go back here, probably easier here. I don't have the comparison here, but you see the dots and the the straight lines, right?
Yes.
This is the first application of the method. The method was first applied to a real system in this case. The distribution of couplings that was used here has 0 parameters. 0 parameters. You measure the density of impurities, and you deduce theoretically the distribution of T's, because this is a T problem. So this is a problem where you have, okay, this is for the spins, okay? So this is a problem where you have J's between the spins. And actually, there's not even first cousins, first neighbors. This can be any neighbor. And this guy goes like T squared divided by U, and T is exponential with the distance. And this is, there is a certain length here. This is gotten from the incredible knowledge that we have about silicon.
No, but what is P of J? So that's the part that
So
confused me.
I know where the guys are, right? Because
Yes.
you take a 3D sample and you throw them there. Okay, so the distances vary. So depending on the distance, you have a different T between them. And the J's are basically proportional to T squared. And there's no, it's incredible, this thing. There's no fitting parameter.
No, I understand, but P is not, you're not using P of J. You're saying, I know where the impurity is, and I know
That's
how
right.
J
I have the
depends on it.
distance here.
Right.
I put it here, then put it here, and put it there.
But you don't have an ensemble of H's like you were doing.
You do, because if your sample is here,
If you move T, you say.
you put
Okay, okay.
5 impurities.
No, I understand.
If I put 5 impurities now, it's going to be different.
No, I understand. Okay, okay, thanks.
I have a very general question about the range of applicability of the strong disorder renormalization group. What class of models and systems do you expect this to be a good approach to?
Okay.
That's very broad. That's
No, it's a great question. And there are many answers I can give. More physical ones and less physical ones. But so let's start with the less physical ones. If you take your model and apply it, you apply it blindly, and you look at the distributions. I showed cases where it becomes broad, okay? That's sort of the best case scenario. If you do the same problem for spin 1, just change spin 1/2 to spin 1. And if the initial disorder is small, it does not broaden. And we know physically what's going on. Spin 1 is a famous Haldane system, for which Haldane got the Nobel Prize, where he showed that this is a gapped system. So you expect the gap to protect the system against weak disorder. And the method tells you that, because the distribution does not broaden. Now, if you start from an initial distribution that's wide enough, then it's going to broaden, and the physics is the same. But this problem with spin 1 has a different phase diagram, okay? It has different phases. The spin 1/2 one just have one phase, okay? So one thing that I can tell you is what I'm saying right now, which is if the distributions become broad, then the method is justified a posteriori, right? Because the perturbation theory is good. Of course, you don't know if the beginning of the procedure is all right, because at the beginning you're making mistakes. You don't know if this is justified. But the thing is that you can analyze close to the other fixed point. You can analyze if it's attractive, and you know that there is a chance that if the initial disorder is large enough, you go there. Whether for smaller ones you go or you don't go, you don't know. Okay, because the method is good at strong disorder. It's tailored for the analysis of strongly disordered system. This is, when you work out the distribution of these guys in real systems, extremely broad, like 7 orders of magnitude, values of J. Okay? So this is one answer is this one. You look at the distributions and you see if they get broader or not. Now, there is another more physical thing to say, which is the following. You remember that here I form singlets, right? I didn't show the picture here, but you can look at the ground state. For instance, these 2 spins, you form a singlet, and then you renormalize the distribution, and then later on you form a singlet with these guys, and then you form a singlet with this guy. This is a so-called a random singlet phase, okay? Or Valence bond glass, sometimes people say, okay? But the excitations are breaking these bonds. So the longer bonds are the most weakly coupled. The longer, the more weakly coupled they are. So if you raise the temperature from 0, you start breaking these long bonds. And the excitations are these triplets that you form, these free spins that you form as you break the bonds. But the excitations are all localized. Right? If you break this bond, you get a spin here, a spin there. Okay? They're localized. The spin that's here or over there doesn't see this guy. So the method is usually works when there is some form of localization in the problem. So if not, it's more complicated. Okay? But that's a more physical answer to your question.
Thank you.
Okay, I have 2 questions, and the first one is because you show a system that you have both attracted and repulsion interaction. So my question is if you have some feeling about the realistic system that have some, I don't know, in the transition.
There's one way out there for this, which is the following. There are certain atoms which are called negative U centers. I know bismuth is one of them. It's when you go across the periodic table and you close a shell, you close this, for instance, the 2s shell, the 2p shell, is a very stable configuration, atomically stable. And so if you are 1 electron shy of a full shell, the next electron is very stably accepted there. So these are situations where this is called a negative U center. Okay. So if you look at the energy of the states as you put electrons, it goes down, and you put the next one, it goes up. So it's as if this guy wants to have that electron. Depends on how you start counting, but it's better to have this guy than to have this or that guy. So it's a negative U center.
Okay, but
there are a few atoms that are like that. So if you have one possibility of having this kind of situation is if you have mixed impurities, which are some of them negative U type and others positive U type. This is a long shot, okay? I'm just saying that that's the only example that comes to my mind that might have this kind of physics. It's not completely crazy, I think.
Okay, my second question is about, because you just use the system that you can map in an interactive system.
No, that's not necessary. It's just no. For instance, if you start with spin 1, Jordan-Figner doesn't work. So, but you can still do spin 1.
So
I just did that because I wanted to give a feeling for a fermionic system that has this behavior. But
so that's my question. So you can have something like analogies to the multi-level one-so impurity model without the term of the interaction?
You're coming back to Anderson impurity interaction, but this is a different problem. This is a different problem.
I just use the Anderson, but you can have the Hubbard model with all the term of interaction. So because you have the on side or something so like that.
That's
you can have here. That's my question. So
that's the kind of thing I wrote down here, right? This is the kind of system that you're talking about. This is a Hubbard model for spinless electrons. Okay, so this is not the same side, this neighbor side, it's extended Hilbert model without spin.
So it's the same here.
Yeah.
Okay, thank you.
Just a very short question. When you came with the Hamiltonian similar to that from the XXZ model, in the XXZ you started with a system with spins, and then you said that someone very clever has been able to write the interaction as you write it below.
Yes, Jordan did.
Is
Oh, the Jordan Wigner is very old. Yeah, this is very, very old. This is. Yeah, this is very standard procedure. Okay.
Questions? Okay, we can thank Eduardo again.
Thank you.